All right, so we're starting the recording here. And section 2.1, well, what when we have a differential equation, the natural thing to ask is, can we solve the differential equation? And there are many times where you cannot solve the differential equation, okay? But yet we can learn about solutions to the differential equation, and that's what section 2.1 is about. So let me give you a moment to copy this down. Copy this example down. Okay, so of course here we have this differential equation, and the next natural thing to ask is, okay, well, all right, can we solve the differential equation? Can we find an explicit solution for this differential equation? And there are, and of course in calculus 2, when you learned about differential equations that were separable, you could solve some of those differential equations explicitly for y. But there are many differential equations where you cannot. But that does not mean we can't understand something about the solutions for the differential equation. So we're going to draw for this differential equation what's called a direction field. And a direction field shows us qualitatively what solutions look like for the differential equation. So I don't know what the exact solution is for this differential equation. I don't know it. It's not separable, so to solve it, we'd have to use another technique. But let's go ahead to the next page. What I do know is I have the differential equation, and I'm going to make use of that. So here on this page, what I've done is here's the differential equation, and I'm going to pick helpful values and equations so that I can graph the direction field for this differential equation. So like for instance, since dy dx is equal to x squared minus y squared, oh well, okay, suppose I were to consider points where y equals x. Okay, for those points, dy dx would equal 0. Okay, because just substitute x in for y, and you're going to get dy dx equals x squared minus x squared. So dy dx equals 0. Similarly, if y equals negative x, dy dx will equal 0. And I'm going to give you a chance to copy this all down because we need to draw the direction field. We don't have it drawn yet. And then I decided, well, what if x were equal to 0? If x were equal to 0, okay, and I substituted in 0 for x, I would get dy dx equals negative y squared. And similarly, if y were equal to 0, then dy dx would equal x squared. So given these four pieces of information here about the derivative, I can draw a direction field. So let me give you a moment to copy that picture down, and then we're going to fill in our slopes for the direction field. Let me know if you have any questions. Okay, so now let's take a look here. Let's take a look. All right, so let's concentrate on this first piece. Well, hold on here. Let's concentrate on this first piece of information. If along the line y equals x, dy dx equals 0. Okay, so dy dx is a derivative. Dy dx is a derivative. And a derivative geometrically stands for what? A derivative geometrically stands for, that's right, a slope. That's right, Ann. That's right, Justin. So what I'm going to do is along the line y equals x, I'm going to draw slopes that look like this. Now, why am I drawing these flat slopes all along the line? I'm sorry, Thomas?
Because there's no slope there. There's 0. They're horizontal.
That's right.
Okay.
Flat lines, horizontal lines have a slope of 0. That's right. And that's right, Andre. Okay. Similarly,
Uh, is there a specific distance where the lines have to be separated, or is it
well,
whatever?
good question, Christopher. When we draw a direction field, we make the I want to say this the right way. I want to determine our slope lines. We make them the same length. Now they're not. I want to be a little careful how I phrase this. And also I'll mention this too. The way the book has it is it actually draws in vectors. Like I have little line segments, but the book will put vectors on those little line segments. But the line segments are signify the slopes, and they make them the same length because that way the line segments don't overlap each other. I mean, to be sure, the slopes are going to, I want to be a little bit careful here how I say this. Depending on where you are on the direction field, the derivative is going to take on different values. So some slopes, if we use vectors have length and magnitude. Well, the magnitude or the length of the vector represents the slope, but the slope value. But we don't want the vectors to overlap each other, so we make the vectors all uniform. What really matters is how these vectors are, what the direction of them is. That's what matters in the slope field.
Okay.
Okay. All right, good question. Now, along y equals negative x, we have a similar situation. The slopes there are also equal to 0. So I'm going to draw flat slopes all along there, all along the line y equals negative x. Okay, and I'll add my arrows best I can here. Okay. So far, are there any questions? All right. Well, the direction field is we want a direction field for the entire xy plane. So let's look at some of our other results here. Now, if x equals 0, dy dx is equal to negative y squared. Well, x equals 0, okay, is that a horizontal line or a vertical line? X equals 0. Is that the x-axis or the y-axis? X equals 0.
Y-axis.
That's the y-axis. That's right, Thomas. That's right, everybody. So there it says dy dx equals negative y squared. So the slope is not constant there. Okay. So let me ask you, at this point here, at 0, 1, what's dy? I mean, that's on the y-axis. What's the slope going to be at 0, 1? Given that dy dx is negative y squared. Okay, it'll be equal to negative 1. That's right, Andre. So I am going to draw a slope like that. Okay, a slope like that of negative 1. What about at this point here? At 0, -1, what would its slope be? That also equals -1. So I'll draw a vector that has a slope of -1. What about here at 0, 2? What's the slope going to be there?
The same.
Horizontal, I think.
Well, this point 0, 2 is on the y-axis, so that falls in this category. It would be -4, because if y equals 2, dy dx is -2 squared, and that's -4. Yeah, well, x doesn't play a role. I mean, along the line x equals 0, there's x, the value of x, well, x is equal to 0. So all you care about is the value of what y is. So in this case now, at 0, 2, the slope is -4. So I'm going to draw a steeper line, a steeper slope. And similarly, at 0, -2, down here, slope's going to be steeper. Okay. So Matthew, we just do the best we can, you know. In what we're going to do is we're going to use MATLAB to verify this slope field, this direction field. We're in Calculus 2, we call it a slope field, but we're going to use MATLAB to verify this direction field. We're not going to draw the whole direction field, but I'm just trying to give you a feel for what's going on when you see a direction field and how you're getting these vectors.
Professor,
Yes, Christopher.
can you explain again how for 2 and -2 it's steeper?
Can I explain again what? How
How the direction field is steeper at those points?
well, when y equals, so what I'm doing here is I'm looking here, man, hold on. I'm looking here at this derivative. So what the dy dx, what happens to the derivative as y gets larger? Does the derivative increase or decrease? As y gets larger, does the derivative become more negative or less negative? That's right, it becomes more negative. So you see at for instance 0, 1, dy dx was equal to -1 squared. So I drew a slope of -1. But at 0, 2, dy dx would equal -2 squared. And so I draw a steeper slope. Similar comments go for the points 0, good, 0, -1, and 0, -2. Good, all right, Christopher. And now let's look at this last piece of information. You're welcome. When y equals 0, dy dx equals x squared. Well, y equals 0, we know that as the x-axis. So there, like for instance at x equals 1, okay, the like I should be more clear, at 1, 0, dy dx would be 1 squared, and so your slope is going to be a +1, and so here's the vector there. And then at -1, 0, the slope is going to be also equal to 1. Okay, and so, okay, so when we draw a direction field by hand, we try to pick certain characteristics out about the from the derivative that we're given to graph the direction field. But of course, the direction fields can get pretty complicated. So what we're going to do is we're going to use a MATLAB program to help us graph the direction field. And what I've done is in Blackboard, there is a folder called MATLAB Programs. And what I'd like to do is go to that folder and show you the program and actually run it for you. So are there any questions so far? Let me turn off that. One moment here. Sorry, class. Let me just, okay. Okay. All right. So let me go into Blackboard. Stop sharing here. So we have a feel kind of for what this field does, but you know, there are a lot of other points we haven't looked at, but you know, so let me go into, hold on here. Yeah, into Blackboard. Is everybody seeing the Blackboard okay? Maybe give me a few thumbs up. Okay, thank you, Andre. Thank you, David. David, thank you here. It's good to have you here. Good to have everybody here. All right, so, all right. By the way, David, just quickly to mention, if you go to course information, you can find out the class key that will get you into WebAssign for homework and so forth. So, all right, you're welcome. You're welcome. Okay, here's what you do. You click on MATLAB Programs, and then there's a link here. Click here to see MATLAB programs that will be helpful. I'm going to click here, and up comes, okay, section 2.1. This MATLAB program will help you draw direction fields. So you click on the link, and then you'll see that, you can't maybe see it, but if you try it, you see on like the bottom left corner of your computer, it has a MATLAB program that was downloaded. You all see that? I mean, you should try this with me. Everybody should be trying this. Does everybody see there's a MATLAB program that got downloaded? Okay, and of course you should install MATLAB. You should install MATLAB. You know, if you haven't done it, you should do it today. But when you click on that link, it will download a MATLAB program. And if you click on the MATLAB program, it will open up MATLAB and produce, and then you'll see the MATLAB program right there in the editor box. Okay, so I clicked on the MATLAB program, and since I have MATLAB installed, I can open up the MATLAB program. But you have to get MATLAB installed on your computers in order to open up the MATLAB program. Okay, so when you do that, let me go ahead and let me go here. Hold on. This is what you'll see. This is what you'll see. This is the program. Now this program, see, it brings it up in what's called the MATLAB editor. And so this program is used for section 2.1, exercise 1, which corresponds to the example we're doing. There's code in here that I don't want you to, like the quiver command is to draw the arrows. And in the quiver command, the reason you're taking, dividing by this L is so that the lengths of the vectors are all uniform length. There's a lot of code here that you don't really need to worry about in terms you won't need to change it. But what you do need to change when you work on your section 2.1 assignment, when they ask you to draw a direction field, and the calculator, TI-84 calculator, won't be good enough to do it, is this right here. This here is your differential equation. So our differential equation is dy dx equals x squared minus y squared. Well, in the program, instead of dy dx, you use the letter a capital S. Okay, but this is what you're going to be changing for different problems. Okay, and also you'll notice that there is a dot before the exponents. There is a dot before the exponents. The reason that is MATLAB is used to do matrix math, but we're doing pointwise computation. So in MATLAB, if you were to just take like x squared, it might think you're trying to multiply two matrices, x times x. We don't want it to do that. We want it to evaluate the derivative at different points that are created in this mesh grid here. This mesh grid command above, here creates a 3x3 window. Okay, like x-axis goes from -3 to 3, y-axis goes from -3 to 3. That's and with an x scale and y scale of 0.3. That's what the mesh grid is. And then this command here is for the differential equation. But if you ever have problems with, well, like let's say you have a problem where you have to do the cosine of x squared. Your differential equation, say, is dy dx equals the cosine of x squared. And you're wondering, well, how do I type a cosine in MATLAB? All you need to do is on this command window here, you see this little fx feature. You just click on that. It says browse for functions. You click on that, and it'll open up a help menu. And in the help menu, you can type, like for instance, you can type cosine and enter, and it'll bring up cosine, and it'll have examples where, how do you do the cosine? So cosine in MATLAB is COS, but then you need a parentheses x. Okay, so you're going to be using that little feature. But that being said, let's go ahead. Let me show you here how this works. So all you need to do is copy the code here, copy and paste it on your command line, and then hit enter. And there it brings up the, let me see if you're seeing it. It brings up the, it'll produce the graph. The graph that got produced, let me just show it to you, because I have to, here's the graph that got produced. That's your direction field. And you can see that the direction field, yeah, you could, hold on, you could use run also. You could use run. There's a thing for, sorry, let me bring that graph back. There's a thing for run also in the command line. I have had, oddly enough, hold on, I might have to do this again, hold on. All right, so I got to always double check. All right, I'm sharing the window here. This is all being recorded. If you type CLC here, it will clear the command window. Okay, and if you can type run. But here's the thing: I get messages, and it has to do with folders and things. It has to do with where I stored this program in my computer. So hey, look, I have a way that works. Copy and paste. It works, and I'm going to go with that. But you can indeed explore other ways. The run command should work, given certain things. So, all right. So let me just see here. Back to. Oh, you need to save it, Michael, first. You need to save the program first. All right. Well, I'll let you all examine that. Andre likes that. He likes what he's seeing. Thank you, Andre. And let me just go.
I have a quick question.
Yes, one moment. Let me bring up that direction field.
Yep.
All right. So so the direction field. Oh man, I keep. Hold on here. All right. So the direction field. Hold on here. See, I'm trying to get it. Are you all seeing a nice picture? Who's seeing a nice
Yes.
picture? Okay, good. So you can see it fills in the gaps, but you can see what we drew by hand jives, corresponds nicely with the direction field. Yes, Christopher, question.
So is it MATLAB meant to help us for the homework on WebAssign, or is there a different homework?
It is to help you with section 2.1. You will need to use it for section 2.1.
Okay.
I mean, what I'm trying to say is I'm not saying you can't do direction fields by hand, but you're going to be thankful you have MATLAB. Let's put it that way. And also, let me just see here if there's anything else. Remember, hold on here. I'm going to do one more example here. Now, also, you can draw solutions on the direction field. You can draw solutions on your direction field. So, let me just see here. One moment, class. I'm going to bring up, I think I'm going to bring up the ebook here. Okay, good. Let me bring up the ebook and find. Yeah, so you see here, like in this figure 2.6.1, they've drawn a direction field, and then they've drawn a solution that passes through the point 2,4. So remember, you solved initial value problems where you were given a derivative function, you were given a differential equation, you were given a differential equation and then an initial value. Okay, well, that yielded a solution, a unique solution. Okay, normally if the conditions are right. Well, that corresponds nicely. Oh wait, hold on. I'm in the wrong. I want to be in section 2.1 here. Hold on. Okay, that corresponds with what you see in section 2.1. So like for instance, here they have solution curves in figure 2.1.2, solution curves following the flow of a direction field. So you have a direction field and then solution curves to the differential equation have to follow the direction field. Okay, they have to follow the direction field. So you can see on this picture here a direction field in figure 2.1.2. Here's a direction field with 3 different solution curves, and each solution curve passes through a different point. So in your WebAssign homework, in addition to getting the direction field, you'll be given pictures where you have to match. You have to have the right direction field, but then you also have to have the direction field that's correct, along with solutions that are drawn correctly on the direction field that pass through the appropriate points. Okay, so you'll see that as well. All right, so on that note, let's continue on here. Let's continue on. Okay. Okay, let's do another example here. We're going to talk about something called a phase portrait. So let me give you a moment to copy this example down. Yes, Matthew, there will be MATLAB assignments, and they will be coming. Right now, you're not ready to work on them yet. We have to get a little bit more into the course. This is like for the first day we've been using MATLAB. But yes, they will be coming. And when you work on your MATLAB assignments, I will let you work in groups, and groups of 3 or 4. And actually, you'll be given some extra credit if you work in groups on your MATLAB assignments. Okay, but that's down the road. All right, so let me let you copy this example down. Okay, so in this problem, we have what's called an autonomous differential equation. Autonomous means that the right-hand side of the differential equation, which, you know, you're used to thinking of that as dy dx equals some function of x and y. Well, our function of x and y is y squared minus y to the fourth. But the right-hand side is a function of y only. It's independent of x, although y is understood to be, I got to be a little careful how I say that. Y is a function of x, but the right-hand side is independent of x in the sense that there's no x term on the right-hand side. So we call this an autonomous differential equation. And they come up in a lot of applications. You saw those kind of applications, for instance, in Calculus 2. And what we want to do is we want to sketch graphs of typical solutions using a phase portrait. So here, yes, I could put this in. I could draw the direction field, but I'm not looking for the direction field. I'm looking to see. Well, I want to be a little careful how I phrase it. I'm just looking to find typical solutions. I'm not looking to see the direction field. Okay. All right. So Paige, just maybe go log out and come back in, and maybe that'll solve the problem. Can everybody see the page? Matthew, you can see the page okay? And all right, David can. All right, wonderful, wonderful. All right, so let's go ahead to the next page then. So what I do is I'm going to take the right-hand side of my differential equation and factor it. Okay, I'm going to factor it. So dy dx equals y squared times 1 minus y squared. And what I'm going to do, well, and I've drawn a picture here. Let me give you a moment to copy that picture down. Okay, let me give you a moment to copy that picture down. We might run over a few minutes if you can stay. I mean, we shouldn't run over more than 5 minutes, and it'll be in the recording. But if you can stay 5 minutes past 6:15, I'd appreciate it. If you can. If you can't, I understand. All right, so take a moment to copy the picture down. Thank you, Thomas. Okay, so, all right. Now, what I've drawn here, let me ask you. Let's consider the point 0, 1. What's dy dx equal to when y equals 1? What does dy dx equal to?
0.
0.
That's right. So if we have an initial condition, good, of 0, 1, that means that dy dx equals 0. And so that means that the solution passing through 0, 1 would have to be a flat solution. In other words, this is the solution, y of x, to the differential equation that passes through the point 0, 1. And similarly, 0, negative 1, you're going to have another flat solution. Those are called equilibrium solutions, by the way. Solutions that where the derivative equals 0 are equilibrium solutions. So I have two potential solutions. I have two solutions, and I haven't solved the differential equation. I'm just looking at, but I'm looking at the differential equation. Now let's take a value here. Let's take a value here. Let's say you have the point 0, 2. In other words, I want the solution to the differential equation that passes through the point 0, 2. Okay? One moment. Okay, so what can you tell me about the derivative at this point? Is the derivative positive or negative when y equals 2?
Negative.
Right. Well, and that is correct, Thomas, because if you substitute in y equals 2 here, yes, y squared is going to be positive, but 1 minus y squared is going to be negative. And in fact, for any y value greater than 1, the derivative is going to be negative because of the 1 minus y squared term. And so that means that if the derivative is negative, what does the solution have to do? Does it increase or decrease? If the derivative is negative, it decreases. So this is what solution would have to look like up there. All the solutions who have y initial values greater than 1 would look like that. And down here, all solutions that have initial values, well, like if this were, say, it always helps to think of a point, like 0, negative 2. If that's your point there, okay, what would the solution have to do? Still decrease. So it would have to look like that. Okay. And incidentally, we do have another equilibrium solution here at 0, because when y is 0, the derivative is 0. There's another equilibrium solution. What if your solution, what if your initial condition, what if y of 0 was equal to a half? Okay, so let's say the initial condition, we want to know what the solution looks like that passes through 0 and a half. That's right, Matthew. It would have to be increasing. Just take a half and substitute it into the differential equation. You're going to get a positive number. So this is what the solution would have to look like. It would have to look like that. You know, that's another. So we're graphing solutions to the differential equation for different initial conditions without solving the differential equation. but we can qualitatively see what solutions look like. And then finally, I pick nice values. If we had 0 and -0.5, their solutions would also be increasing. So this is called a phase portrait. How many think phase portraits are pretty cool?
Yeah.
Okay, Justin likes it. Well, great. Are there any questions? Are there any questions? Okay, all right. Well, I'm going to stop the recording. I thank you all for staying the extra time.